Welcome back. Topic of today's lecture is going to be Hartree-Fock. We're considering systems of interacting fermions. Before launching into Hartree-Fock, which is a pretty big subject, let's do a little bit of review of what we discussed last time about interacting fermions. So we wrote a general Hamiltonian as a non-interacting piece plus an interacting piece. And this general Hamiltonian we're going to work with, it could work, we could be applying it to electrons, to neutrons in a neutron star, to electrons in an atom. It could be electrons in a metal. It could be electrons in a two-dimensional electron gas. It could be helium-3 fermions in a fluid. Really, it's really any fermionic system where we have just free fermions and a interaction between them. Very, very general problem that a lot of people have to worry about independent of your field. The non-interacting Hamiltonian we can write as very generally a single body part, C dagger alpha C beta with some coefficient H alpha beta, and it's sort of typical to choose to work with the diagonal form, sum over A epsilon A naught C dagger A C A, but you're not required to work with the diagonal form. It just makes things easy to do. The interacting part we can write very generally for any two-body interaction, density interaction, sum over alpha beta gamma delta, V alpha beta gamma delta C dagger alpha C dagger beta C delta C gamma, and note again the ordering here is opposite the ordering here, and that has to do with making sure that everything comes out. We don't lose minus signs, and we don't lose extra minus signs when we commute operators through each other. Okay, so this matrix element V, let me make myself a little smaller here. V alpha beta gamma delta, we can write out explicitly if we wanted to, A alpha beta gamma delta as integral d1, integral d2, psi star alpha 1, psi star beta 2, V of position 1 minus position 2, phi of gamma 1, phi of, I keep calling it psi, don't I? Phi delta of 2. So we're going to probably, when we actually start getting down to really doing calculations, we probably want to keep track of what this matrix element is, maybe calculate it for different types of interactions we're interested in. We can, if we want, we can write this also as, I guess, alpha beta V gamma delta. One thing to note, there's a symmetry of this interaction, that V alpha beta gamma delta is V beta alpha delta gamma. That's just exchanging all the 1 coordinates for all the 2 coordinates, and they're dummy coordinates anyway, so it doesn't matter if you write alpha beta gamma delta or beta alpha delta gamma. We're going to use that symmetry later on at some point, so we have to keep it in mind. Anyway, in last lecture, we did first order perturbation theory, first order PERT, where we just calculated the expectation value of the interaction Hamiltonian. You worked in the basis where the non-interacting part is diagonal, and we wrote the expectation of the interacting part of the Hamiltonian, 1/2 of the sum over orbitals A which are occupied and orbitals B which are occupied, and there were 2 terms, VAB AB minus VA BB A. This is the Hartree term, our density interaction, Hartree, and this was the Fock term. And notice that the Fock term comes with a minus sign. So if the Hartree term is a repulsive density-density interaction, like Coulomb interaction between two electrons, the Fock term will be attractive. Comes in with the opposite sign. Also, as I mentioned, that in order to get a non-zero Fock term, orbitals A and B have to have overlap both in spin and space, which often means that the Fock term is short range, because the actual wave functions between orbital A and orbital B have to overlap to give you a non-zero result. Okay, so with that as an introduction, we want to consider a better approximation than first-order perturbation theory, which is Hartree-Fock approximation. But before doing Hartree-Fock approximation, I'm going to review something that we learned in solid-state physics last year, or you should have learned in solid-state physics last year, or in earlier years, which is the idea of mean field theory, because Hartree-Fock is a mean field theory. So let's recall what we learned about mean field theory. So probably we introduced mean field theory in the context of magnets, or magnetism. You might have some sort of Hamiltonian, which is sum over I and j of j si dot sj, or something like that. The sort of Heisenberg type Hamiltonian, and generally it's not so easy to find the exact ground state of a Hamiltonian, which has interactions between sites I and j and lots of different spins. So the way you handle it is by taking one of these spins and averaging it, taking the mean value of one of these spins and leave the other one unaveraged. So you'll take the Hamiltonian on site I is going to just be j si dotted with the average of all sites j, average over all space. So this is a very simple, so S average here, this is a scalar, as is j here. So we can then, we just have a single site problem, and we know how to calculate the properties of a single spin, potentially in a magnetic field. Here's the S here is acting as an effective magnetic field. So we've calculated its properties, and then the last step of mean field theory is the self-consistency step, sometimes called self-consist, so as if it was a verb. We want to self-consist. I'm not sure that's actually grammatically correct, but we then want to have the situation that when we calculate the expectation of SI at the end of the day, it should equal the expectation of Sj that we used here. Okay, so that's the self-consistency step. Okay, that's how mean field theory generally works, and we've used it in magnetism, and probably learned about how you can have phase transitions and so forth. How do we apply that to Hartree-Fock? So Hartree-Fock is a mean field theory. Hartree-Fock is a mean field theory that works in the following way. We don't know how to deal with the interaction term of the Hamiltonian, which I'll write out again: alpha, beta, gamma, delta, C dagger alpha, C dagger beta, C gamma, C delta. Oops, I didn't write the V. Here, let's just move this over. It's amazing you can do that. Incredible editing. Alpha, beta, gamma, delta sitting here. So we don't know how to deal with a 4 fermion term here, but what I can do is I can take an average of two of these terms, a C dagger and a C, and leave the other two unaveraged. Okay, that's the scheme of writing our effective Hamiltonian. Effective Hamiltonian will be same 1/2 alpha, beta, gamma, delta, and now I'm going to take the average of two of these operators, one C dagger and one C, at a time, and leave the other two unaveraged. So we'll write this as, I guess, C dagger alpha, C gamma, C dagger beta, C delta, and then there'll be a term plus C dagger beta C delta, C dagger alpha C gamma, and then on two more terms, and they come with a minus sign, C dagger alpha C delta, C dagger beta C gamma. And the reason these two last terms come with a minus sign, C dagger beta C gamma, C dagger alpha C delta, the reason they come with a minus sign is because in order to commute, so let's take this term here, in order to commute the delta all the way through so that it's next to the beta, oops, so it looks to me like I made a mistake here. Yes, I did make a mistake. That this should have read C delta C gamma here, because gamma delta should be in the opposite order of delta gamma, as I emphasized before, so I messed that up. And now it's correct that if let's look at the first term here. In the first term, I average alpha and gamma, and in order to bring the gamma next to the alpha, I have to commute through two operators, so I get a plus sign. Whereas in this third term here, in order to commute the delta next to the alpha, I have to commute it once, so I get a minus sign. Okay, is that clear? I hope. All right. So there's one more thing that we're going to notice, and remember that there's a symmetry of the oh my gosh, I left out a V also, so let's put in V. I guess V alpha beta gamma delta times the whole thing. Okay, so there's a symmetry of V alpha beta gamma delta, that V alpha beta gamma delta is the same as V beta alpha delta gamma, you may recall, and that means that these two terms are the same as each other, and these two terms are also the same as each other. Okay, so hopefully without making further mistakes, we end up with our effective Hamiltonian. Effective Hamiltonian, I can write it as sum over gamma delta alpha delta C dagger alpha C delta, where this object F, alpha delta, is just sum over beta gamma, expectation of C dagger beta C gamma times V alpha beta delta gamma minus V alpha beta gamma delta. Okay, and let me make this a little smaller so you can see everything at the same time. There. Okay, so the two of the sums are here and two of the sums are here. The expectation is always put here. V is here, and then an order of the V gets switched. Alpha beta delta gamma here and alpha beta gamma delta here with a minus sign. Minus sign there. Okay. So this is now our mean field Hamiltonian, our total Hamiltonian. So this is the effective Hamiltonian. Maybe this is the effective Hamiltonian for the interaction part only. Let me just write that in. So the total Hamiltonian, the total effective Hamiltonian, H effective total, is going to have the one-body term, alpha delta, plus F alpha delta, and then C dagger alpha C delta. So this is the part that I had, just the regular one-body term, and this is the effective one-body term that we get by averaging two of the operators in the 4 fermion interaction. So these things end up giving me a scalar. So these equations here constitute the Hartree-Fock equations. All of these. Well, actually, I don't even need this. It's just these two, actually, that constitute the Hartree-Fock equations. I'm going to use those a lot, I guess. So the way you actually implement Hartree-Fock is you want to get to a self-consistent solution of these two equations. So how do you do that? Well, what you do is you can follow a couple of steps. Oops, not in red. Let's make it in black. One, let epsilon mu be the eigenstates of H alpha delta plus F alpha delta. Okay, with eigenvectors, call them mu. Okay, E mu and mu. What we want to do, step 2, is we want to write creation operators for these eigenvectors. So we'll write C twiddle mu. This is a new basis. We know how to change bases. C dagger alpha like this. Okay. Now in this basis, the Hamiltonian is really simple. H equals sum over mu, epsilon mu, C dagger twiddle of mu, C twiddle of mu, diagonal in that basis, which is good. And so we can fill the lowest n states with electrons if there are n fermions in the system. Fill lowest n states, which we can write the wave function if we want. Psi, our new state, is going to be filled the lowest n eigenstates, like this. And then step 5 is to self-consist. Meaning recalculate F and go all the way back up to step 1 until you converge, all the way back up to step 1, and until it converges. And remember here that F is some expectation, but once I know what wave function we're considering, so we decided the wave function is here. Once we've defined our wave function, we can calculate these expectation values and then recalculate F, and then we self-consist until the whole thing converges. Now, the reason we used we rediagonalized it. We don't actually. It wasn't absolutely necessary to switch into the eigenbasis and in step 2 here. We could have worked in any basis we like, but it's particularly convenient to work in this diagonal basis, because in this diagonal basis, C twiddle dagger mu, C twiddle nu is really super simple. Why? Well, because we just have a whole bunch of filled orbitals in this wave function psi. We have a bunch of filled orbitals and a bunch of empty orbitals. So this thing is going to be just delta mu nu times 1 if mu is filled and 0 if mu is empty. Which means we can write out F, recalculating F in really easy. It's just the sum over mu occupied of V alpha mu delta mu minus V alpha mu mu delta. Okay, so that's why we like to rediagonalize into this diagonal basis and at each step. Now, so we repeat this process over and over. We go back to the beginning. We define a new basis, the diagonal basis of F plus H, switch everything into that basis, fill up the lowest n fermions in that system. We then have, we have our new ground state, we have our new trial wave function, recalculate F, go back up to the beginning again. Now, how do we know when this converges? At convergence, then things stop changing. You get the same answer in each iteration. That's what convergence means. It no longer keeps changing, which means that H plus F is diagonal when we recalculate it. Which means we don't have to rediagonalize because we're already diagonal because everything has stopped changing. In which case, the eigenvalues are just H mu mu plus F mu mu, or we can write it as h mu mu plus sum over, maybe I'll write it this way, orbitals nu occupied of v v sub mu nu mu nu minus v sub mu nu nu mu. And you'll recognize these as being Hartree and Fock terms. Okay. All right. So that's what happens when you get to the end of the calculation. That we have found this wave function. We found a single wave function here, psi, which we've written as a single Slater determinant in a certain basis. And when we plug it back in, we've discovered that it's self-consistent. Everything's diagonal. And these are the energies E mu. Now, what are these energies E mu? These E mu's are actually are known as the Hartree-Fock ionization energies. They are the energies to remove one fermion from the system from orbital mu. Ionization energies. And the fact that these E mu's are Hartree-Fock ionization energies is known as Koopmans theorem. Koopmans. The S is part of his name. His name was Tjalling Koopmans in Dutch. I'm probably not pronouncing his name well, but anyway, his name was Koopmans. Koopmans discovered this in 1934, very, very early in the history of quantum mechanics. He was age 24 at the time. You may not know the name Koopmans already, but he's quite famous. He's actually a Nobel laureate, but his Nobel Prize is in economics, actually. He, very shortly after doing this work in physics, he decided to switch fields into economics, where he became quite famous in that field. He won a Nobel Prize in 1975, much, much later, in economics. His work was on something like the optimal allocation of resources in economics. The joke, of course, is that his resources were better allocated to economics than they were allocated to physics. But anyway, this Koopmans theorem is quite an important theorem in physics and in understanding Hartree-Fock. Also, I think one other sort of random comment. Koopmans, I was told that Koopmans is the Dutch word for merchant or a trader, which sounds like it's something that economists should be interested in, I guess. So maybe that's why he switched. Okay, anyway, the total energy of the Hartree-Fock state, E total in the Hartree-Fock state, is given by the sum over the filled orbitals, occupied orbitals, of h mu mu, because we're in this diagonal basis, plus 1/2 f mu mu. And you might wonder, if I look up here, the E mu's here are h mu. The ionization energies are h mu mu plus f mu mu, and here to get the total energy, I have h mu mu plus 1/2 f mu mu. And this 1/2 is there to prevent overcounting. The reason being that when you calculate an ionization energy, you're calculating the interaction energy between the particle in site I that you're removing from the system and all of the other particles in the system. So the particle mu, the particle in orbital mu, you're calculating its interaction with all the other particles that are occupied in the system, all the other new orbitals that are filled. However, if I'm trying to calculate the total energy in the system, I only want to count 1/2 of that interaction energy, because half of the interaction energy belongs to particle mu and half of the interaction belongs to particle nu. Otherwise, I would calculate the energy of mu interacting with nu and also the interaction of nu interacting with mu. So that's where this factor of 1/2 comes from. Okay, so this is the definition of Hartree-Fock, but I'm going to claim an equivalent definition of Hartree-Fock, approximation is the best variational. When I say best, I mean variational calculation. Variation. Let me just write it again. I think it was correct, but variational single Slater determinant wave function. Okay, so if you consider all possible single Slater determinants. It's only one single Slater determinant, but you can, any orbitals you want in that single Slater determinant. The single Slater determinant that gives you the lowest possible energy is the Hartree-Fock wave function. In other words, the product over mu filled of C dagger mu on 0, that's a single Slater determinant. And what we've done by following this Hartree-Fock prescription is to find the best possible orbitals to fill so as to lower the energy as much as possible. Now, the proof that this is equivalent to the self-consistent calculation we just did is a bit subtle and maybe even a bit complicated, but it's worth going through because I think you want to learn something by doing it. So let's do it. The wave function we're going to consider is this filled Fermi C. I'll just write it here. The ground state, it's called ground state 0, is going to be this filled Fermi C, and we're going to fill up, lowest n states. If I have n orbitals, so I have the energies of these states like this. They'll be filled. Maybe here's the chemical potential, and then I have a bunch of empty states here. Okay. This is the wave function I want to consider. I just want to figure out what these orbitals are, which I'm putting below the chemical potential. Now, my claim is that what we just calculated is going to give me the best possible orbitals down here. And the general strategy here is going to be to do the following. We are going to change our basis a little bit so that we change what these orbitals are representing. And we want to show that as we change what these orbitals are representing, the energy goes up. Or strictly what we're actually going to show is that we are at an energy extrema of when we write down a wave function like this that has solved the Hartree-Fock equations that we just derived. Okay, so we're trying to show that the Hartree-Fock equations we just derived give us a ground state wave function such that if I try to vary any of these orbitals, what's contained in these orbitals, I am going to, well, you want to be at a minimum, but what we're strictly going to show is that we're at an extrema. Okay. So the way we do this is we're going to imagine changing the basis. Imagine a continuous basis change. And the basis change, we'll write our C dagger, alpha. A dagger like this, it will be sum over mu, exactly the same way we always change basis. Mu alpha C dagger mu, and we can write that as a unitary matrix U alpha mu C dagger mu with the sum over mu implied. So we want to consider all possible unitary matrices here and show that if we vary the basis at all by any non-trivial unitary matrix, I'm going to increase the energy, or I'm at an energy extrema. Okay. Now, one thing to notice is that any rotation or change of basis, unitary rotation or change of basis, which only mixes filled with filled, or empty with empty, or empty with empty, leaves the wave function unchanged. The many-body wave function unchanged. Many-body wave function unchanged. Slater determinant, possibly up to a definitional minus sign. So, I mean, this is something that you know is maybe natural physically. I have this picture here with a whole bunch of filled orbitals and a whole bunch of empty orbitals, and if I make some sort of change of basis such that these two empty orbitals get mixed with each other, well, the wave function stays unchanged because these two are both empty, and it doesn't matter if I'm mixing them. And similarly, if I take two of these and I mix them with each other, well, I'm filling them both anyway, so it doesn't matter how I represent the basis of those two orbitals. So actually, we can be a little bit more definitive about this. For example, if we write C twiddle A is, I don't know, C dagger 1 plus C dagger 2, 1 over square root of 2, and C twiddle dagger B is C dagger 1 minus C dagger 2, 1 over square root of 2. That's a unitary transformation. You can check that that the wave function that you create with C twiddle dagger A and C twiddle dagger B on 0 is the same as C dagger 1, C dagger 2 on 0. Okay. It may be up to a constant, but you know we normalize the wave functions anyway, so it doesn't matter. Okay, so that's one thing we have to worry about. So we're only going to be, you know, when we write down some sort of arbitrary basis change here, and we want to show that our energy is extremized under any such basis change, we only really want to consider basis changes that mix filled states with empty states. So those are the non-trivial ones. If I mix filled state here with an empty state up here, then I'm actually changing what the Slater determinant is representing, and actually I do something physically non-trivial. So that's what I'm concerned with. Further, okay, so I want to think about unitary transforms, and I want the unitary transforms. I want to consider small unitary transforms because I'm trying to do a differential calculation to show that I'm at a minimum in energy. So I'm trying to make a sort of a small change in the basis and see that the energy goes up, or show that I'm at the bottom here. So to make think about unitary transforms that are small, in other words, close to the identity. So we'll write our unitary matrix as e to the I epsilon m, where epsilon is small and m is Hermitian. So you will recall that if you exponentiate a Hermitian matrix, you get a unitary matrix. You can sort of check that. E to the I epsilon m, e to the I epsilon m dagger is e to the I epsilon m, e to the minus I epsilon m if m equals m dagger, which is 1. So exponentiating the Hermitian matrix gives you a unitary matrix. Okay, so since epsilon is small, we can expand this exponential, and the unitary is 1 plus I epsilon times m plus ... terms, which we're mainly not going to be concerned with the ... terms. This is going to be enough. So the basis transform that we're going to be considering is our C twiddle mu, our new basis, is going to be our old basis. So this is applying the identity operator to C dagger. That's the first term. And the subleading term is I, sum over nu, well, put the epsilon outside, I epsilon, and then m mu nu times C dagger nu, and then plus higher order terms. Okay, this is this is a matrix, this is a matrix, this is a matrix, and I am applying this equation here. The C dagger in the twiddle basis is the unitary matrix times C dagger in the non-twiddle basis. Sorry about doing all the scrolling. So keep in mind that the only m's I'm interested in M where mu nu, where mu is, say, filled and nu is empty, or vice versa, or nu filled, mu empty. If they're both filled or both empty, it's not going to do anything. So I'm only going to be considering the case where one is below the Fermi surface, one is above the Fermi surface. Okay. All right. So now let's use this expression for my changed operators after I make a unitary operation on them. Let's reconstruct our new wave function. Let's call it psi at epsilon, and that will be, I guess, the product over all my occupied mu's, mu occupied, of c twiddle dagger sub mu on 0. So this is, again, the Slater determinant of my lowest n states, but now I've changed from this just the regular c mu's to the rotated mu's. Okay, and let's write out what we have, what this thing is. Well, we'll plug in this expression up here. So this is now, I guess, okay, so leading term is going to be, well, okay, we'll write it this way. Product over mu occupied, c dagger mu plus I epsilon sum over nu, m mu nu, c dagger nu, all on 0. Okay, now I'm only interested in expanding this to linear order in epsilon. So there's a lot of terms that you would multiply out to get this full product, but I only need to keep track of terms that have a single factor of epsilon. So basically, you take this whole product, and all the terms plus 1 you put in the c dagger here, and for one term you choose this term here. Okay, so the leading term has no epsilons, so it's mu occupied c dagger on 0, mu on 0. So that's the leading term with no epsilons, and then the term with one epsilon will be I epsilon. I'll write it this way. So here I can choose to only use the nu's that are empty. Remember that write that nu empty, because we don't want m to be non-zero when both mu and nu are filled or both mu and nu are empty, because that's rotating either two empties into each other or two filled into each other. So if mu is occupied, then we can choose nu to be empty only. Okay, so we then have a sum over nu empty and mu filled. Okay, and I'm going to write this as m mu nu, c dagger nu, c mu, and then times a factor here, product dagger c dagger mu prime on 0. Okay, so what did I actually do here? What I did was the following. I wrote this term linear in epsilon in sort of a creative way. What I did was I started by writing out the full, so mu prime occupied. I started by writing out the full wave function where you fill up all the mu primes which are occupied, and then I'm going to remove someone from below the Fermi surface and put him above the Fermi surface. Just one, because in this product I'm just going to choose one term with a factor of epsilon, which is going to put someone above the Fermi surface, but it's going to miss someone below the Fermi surface. So it removes someone from below the Fermi surface because he didn't get a c dagger of that mu, and puts him instead above the Fermi surface. And both this factor here and this factor here are the original ground state 0. So I can write, in the end of the day, that my new wave function with a parameter epsilon is my ground state 0. That's from the leading term here. And then plus epsilon times a term which I'll call d psi, and where d psi d psi here is, I guess, I times sum over nu empty mu filled of m mu nu c dagger nu c mu on ground state 0. Okay. So a couple things which are worth noting, that at linear order in epsilon, we have, well, at any order in epsilon, this is sort of genuinely true, that d psi is orthogonal to the ground state 0. Why? Well, because I've taken someone out of the state and put them in another state. So it took someone from below and put them above, so the new wave function is orthogonal to the old wave function. And that's nice because it allows us to say that psi epsilon is 1 plus order epsilon squared. Right? If you square this thing, the order epsilon term will be of this form. So we can drop it. Okay. Okay. So now we're prepared to try to differentiate our energy with respect to this object epsilon, and I want to show that if we've solved the Hartree-Fock equations that we defined in the beginning of this lecture, then we will discover that we are at a minimum already, that there's no derivative with respect to epsilon, usual way of minimizing something. So we'll take d by d epsilon of the energy, so this is psi h psi, and I guess we want to normalize everything, psi like this, but this is really nice. We don't have to worry about the denominator because the denominator is 1 plus order epsilon squared. Since we're only doing things to order epsilon, we can drop the epsilon squared term, and we want to set this derivative equal to 0. And then we actually only have to worry about the numerator being equal to 0 because the denominator has no derivative. Okay, so the ground state being a minimum extrema, actually, extremum of the energy, is equivalent to the derivative of the numerator here being set equal to 0. And keep in mind what the form of the numerator is, ground state plus epsilon. Maybe I'll just rewrite that again because we'll need it. So recalling that psi epsilon is ground state 0 plus epsilon delta psi. We thus have the following condition that taking the derivative here gives me delta psi Hamiltonian ground state 0 plus ground state 0 Hamiltonian delta psi should equal 0, or I could rewrite that as the real part of ground state 0 Hamiltonian delta psi. Equals 0. Okay. So furthermore, this condition which I've written has, remember the definition of delta psi. Sorry, I keep doing all this scrolling. Let's copy this definition of delta psi. Copy and put it down here, where delta psi is this, and this condition. This condition, which is putting me at the minimum of an energy, must be true for any matrix M. So any rotation of my basis that changes the wave function, I want it to increase the energy. So I want to be at a minimum with respect to any M. So that so we can then simplify this even more. That what we really want is the real part of the ground state H, C dagger nu C mu, ground state, should be equal to 0 for all mu occupied and nu empty. Okay, so this actually, I mean, if you look at this condition makes a lot of sense. Let's actually draw the situation here. So we have a whole bunch of filled orbitals here below the Fermi surface, and we have a bunch of empty orbitals here. And the statement is that if I take any particle out of the filled state and mix in any of the orbitals of the empty states up here and calculate and apply the Hamiltonian to it, it should have zero overlap on the original ground state. And that's enough to guarantee me that the wave function that I wrote down here is of minimum energy. Okay. All right. So we're getting close to the completion of the proof. So to complete the proof, I now have to plug in the form of the Hamiltonian here. So let's write this ground state 0. I'm now plugging in the form of the Hamiltonian. I'm going to drop the sums will be implied, I guess. Alpha beta, so alpha and beta are both summed over implicitly. Here, Einstein summation convention, V alpha beta gamma delta, C dagger alpha, C dagger beta, C delta, C gamma, C dagger nu, C mu, on ground state 0. And we want this thing to equal 0. Okay? Okay, well, now it's a matter of calculating this expectation value. Okay, so let's do them. Oops, hang on. What did I do here? This is not C dagger alpha beta, this is C dagger alpha. Stop me, someone yell out. You'd have to yell pretty loud so I would hear it. C dagger alpha, C beta here. Okay, so we have to calculate this, this matrix element, and it has a couple parts in it. Let's first consider the alpha, beta, nu, mu term. Maybe that's the easy one to start with. I'll bring this down here so you can see it. So we want the ground state 0, C dagger alpha, C beta, C dagger nu, C mu on ground state 0. And remember that mu is an orbital which is occupied, and nu is an orbital which is empty. Okay, so this thing, you start with the ground state, which is a whole bunch of occupied orbitals. You remove one of the occupied orbitals and you fill one of the empty orbitals, and you have to get back to the same ground state. The only way you can do that is if beta matches nu and if alpha matches mu. Delta nu beta, delta alpha mu, right? You've removed someone from below the Fermi surface, you put them above the Fermi surface, you have to then remove the guy above the Fermi surface and put him back below the Fermi surface again to get back to the original ground state. Okay, so the first term in this big inner product is nothing more than I'll write this out. The first term is nothing more than h mu nu. Okay, when I take the inner product of this guy with this guy and in between the ground state. Okay, now the second term is a little bit more complicated to calculate. It has 6 operators, so this 4, 5, 6 here. The interaction term here, 6 operators. So let's try to calculate this. This is a little bit more messy. Ground state 0, C dagger alpha, C dagger beta, C delta, C gamma, and then we also have a C dagger nu, C mu, and we know that mu is occupied and nu is empty. So this is occupied and this is empty. Empty. Okay. Well, okay, it's basically the same game. We have to figure out how we can get back to the ground state. Once I started with the ground state, I removed someone from below the Fermi surface, I put him back in above the Fermi surface, and I have 4 operators here, and I have to somehow get back to the original ground state. And there's actually 4 ways to do this. The first way, actually, what I will do is I'm going to copy this 4 times. Copy. Okay, and here we go. Paste. 1. Paste. Let's see if it'll let me paste it twice. Paste. Oh my gosh, this is beautiful. 2. paste 3. I should do all my calculations this way. Paste, one more, paste 4. Okay, all right. So there's 4 ways this can happen. So this is what I'm trying to calculate. Equals question mark. One, and we have 1, 2, 3. Oops, 1, 2, 3, 4. Okay, now I'm going to need to use it. 1, 2, 3, 4. No, okay. I have start with this. Okay, so I have this. Okay, so let's try to match up terms. One way to do it is if mu matches alpha and nu matches gamma and delta matches beta, but delta, if delta is going to destroy something, delta has to be below the Fermi surface. Okay, so I can write this as this thing is then delta alpha mu, delta beta delta, delta gamma nu, but also delta is below the Fermi surface, so delta should be filled. Okay. Okay. The second term, we can. Okay, let's try the second one. We can match up mu with alpha again, and then I can match up nu here with delta and gamma with beta. Okay, so this thing is going to be delta alpha mu again. Now it's delta beta gamma and delta nu, but notice that here, let's see, nu has to be empty, and that means the gamma here has to destroy someone, so gamma has to be below the Fermi surface. Gamma filled. Okay, we already know that nu is below the Fermi surface. That nu is above the Fermi surface and mu is above the Fermi surface. Okay, the third one, we can keep going. That we can now take a different combination where mu matches. Wait! Before I go on, this one comes in with a minus sign. This one comes in with a minus sign here, because you'll notice that in order to bring if I commute the mu all the way through, it has to commute through 4, so that's a plus sign. But now, in order to bring the nu close to the delta here, I need to cross through 1, and that gives me an overall minus sign. Okay, so this one has a minus sign. This one up here had a plus sign. Okay, this term here, I'm going to match up mu with beta. Nu, well, I can match up with either one. Let's match up this one with maybe this, and then gamma can be matched up with alpha, like this. And this one will then be, we can write out the result as delta mu beta, delta nu delta, delta alpha gamma. And there's one constraint here, which is that gamma has to be filled here, because I have to be able to destroy someone when I get to this step. I have to be able to destroy someone when gamma acts. Has to be able to destroy someone. And the last possible term, make sure I get this right. So nu is going to match with beta. This one will match here, and this one will match here. So this will give me delta mu beta, delta nu gamma, delta alpha, and the constraint here is that delta must be filled. And this one comes with a minus sign, whereas this one comes with a plus sign. Okay. All right. So now I've calculated this big inner product, which is what I'm interested in. I'm going to take that inner product, plug it back into here, and then also add to the first term, and what we end up getting is my condition. This is the condition that I wanted to have at the beginning of the day. Let's actually circle it. This was the condition I was interested in. There we go. Oops, that didn't work. Try it again. There we go. That's the condition I wanted at the beginning of the day. Oops. That thing should be equal to 0. And that condition then becomes the following: h mu nu plus 1/2 sum over, let's call it sum over x filled of v mu x nu x minus v mu xx nu plus v x mu x nu minus v x mu nu x. And that whole thing should equal to 0. And we'll again notice that two of these terms, by the symmetry of v, these two terms are the same, and these two terms are the same. So the final condition is h mu nu plus sum over x for the x filled, v mu x nu x minus v mu xx nu should equal 0 whenever mu is filled and nu is empty. And we will recognize that this quantity here, which we just calculated, is actually what we called f mu nu before. Okay? So we've derived the condition that in order to be at a variational minimum of the energy, we must have h mu nu plus f mu nu equal to 0 when mu is filled and nu is empty. What does that mean? Well, it means that any of the off-diagonal terms of h and f have to be 0. The only terms that can be non-zero is so h plus f is diagonal, and if h plus f is diagonal, that means we've come to the Hartree-Fock solution. So our condition that h plus f becomes, we're in a basis where h plus f is diagonal, is the same condition as being at a variational minimum of the energy, and that's what we're setting out to prove. QED, or draw a box or a lobster. You know, there was once upon a time there was a trend among mathematicians to, instead of drawing a box at the end of the proof, they would draw a picture of a lobster. I don't know how long that lasted, but it was there for a while. Okay, anyway, I think maybe we should stop there. We'll do an example, several examples of Hartree-Fock next time, and maybe the lecture afterwards, we'll do another one of the exam problems, because the second exam problem from last year focused on Hartree-Fock, and then we'll finish off the examinable part of the term pretty soon, actually, and we'll be able to move on to the non-examinable part, which is superconductivity, which you can watch if you find entertaining or not, as you see fit. Okay, anyway, until we meet again.